Okay, so we played around with the connection coefficients in a flat space from Cartesian to polar, and now let's move on to curved space. So let's consider a sphere. So as we know, the metric components are, well, let's call it G00 and G11. Looks like that, where x0 is the theta coordinate and x1 is the phi coordinate. So we'll play around with the equations that we get from the geodesic equation for the curved surface of the sphere, and then we'll move to flat and curved space-time versions of the geodesic equation. So let's, again, we want to write down our connections as KFA, as we wrote them before, 1/2 times the inverse BK times derivative of GAB with respect to XF, GFB in XA minus GAF in XB. Okay, so the diagonal terms are 0, and the geodesic equation reads 0 equals, let's start with the 0th coordinate, so two derivatives of x0 in some time parameter, plus gamma 0, 0, 0. So we'll sum. We've seen how to do this. It's the same thing. We'll just write them out. This picks out the x0, dx0. And then we have the 0, 0, 1 and 0, 1, 0 terms. They're both the same. We'll just flip these around, but really we can multiply by 2 here. 0, 1, 0, because these two are the same, so we can multiply by 2. But just to emphasize how they appear, and then we add the 0, 1, 1, and then we just have the x1. So it looks like that, and so now we want to evaluate, as we did before, the gamma 0, 0, and that gives us 1/2 G upper 0, 0 times derivative G 0, 0 with respect to x0 plus same thing minus the same thing. And since the G00s are not a function of x0, x0 is theta now. So let's be careful with that. It's theta and phi, the coordinates. This is a function of r, which is just a parameter. This means that this is 0. Gamma 0, 0, 1 and 0, 1, 0, they're the same. So here we get 1/2 G00, 0, derivative of a cross metric term. We know that's 0 by itself, so it doesn't matter what we take derivative of that with respect to. We have the derivative of that term with respect to x1, and that's also 0 because G00 doesn't depend on the coordinates, minus the doesn't exist, minus the derivative of a component that doesn't exist. That's 0, so this whole thing is 0 as well. And we have gamma 0, 1, 1. So that's 1/2 G 0, 0. The G 1, 0, which doesn't exist, we'll just write it out. That doesn't exist either. Minus, now this term exists, and it does depend on theta, so if we take that derivative, that's non-zero. In fact, we'll get 1/2 times G 0, 0 is the inverse of that, so it's 1 over R squared. And then we take the derivative of this with respect to theta, and that gives us, so in here we have, but there's a minus sign there, so we get a minus 2R squared sine theta cosine theta, and that's just minus sine theta cosine theta. And therefore, we see that our component for the geodesic equation is two derivatives of x naught in this time parameter minus sine theta cosine theta dx1 d tau squared, since this is equal to 0, and therefore we can write it out as two derivatives of theta in this parameter minus sine theta cosine theta d phi d tau squared equals 0. So that's the equation for the motion, for unaccelerated motion for one of the components, the second derivative of theta.